All right, guys. So I want to pick up where we left off yesterday with these linear equations. Now, solving these linear equations, guys, I'm fairly certain that if I gave every one of you a linear equation or a series of them, there would be high proficiency in solving them. Okay. So you might be thinking, you know, some of this stuff is redundant. It's old. I've done this in Algebra 2. I know what's going on. And you're going to see kind of that type of thing a lot in this course. That I've already got a little bit of exposure to this. I understand vaguely what's going on. Okay, or maybe I understand really well what's going on. But I want you guys to start recognizing the reasons why some of the processes that we've been taught in the past work. Okay, because if I understand why they work, then I ultimately understand the properties that are kind of outlining the process, and then in the future, when I come across a question that maybe I struggle with, I can use those properties of algebra that I understand really well to address that maybe new style of problem. Okay, so I'm not so much interested in kind of the monkey see, monkey do type thing, where we could do a question in class together, and then you've seen me do it, so then you can do it. Does that make sense? I'm more interested in you actually learning the system of mathematics and how the rules intertwine and build off of one another and supplement one another. Okay. In addition, I want you guys to understand that there's consistent procedures, whether we're talking about linear equations, quadratic equations, trigonometric equations. There's consistent procedures and patterns that we can use to solve. No, you won't be on that team.
No, like.
It says All-Star.
Did you get that?
I coached the game
a
couple years ago. But there's consistent patterns that we use with linear equations that we'll use with quadratics, that we'll use with cubics, and so forth. Okay. So even though a little bit of the algebra today might be remedial, there are still principles here that we need to make sure we understand. Okay. So we got through yesterday talking about these 6 examples of what's linear and nonlinear. Okay, so linear is obviously there's an infinite number of linear equations, but it's a very small category of all of our graphs. Okay, which is weird that one category of our graphs is called linear, and then every other graph is called nonlinear. Because every other graph we ever come across is not a line. Okay, but they might be parabolas, they might be cubics, they might be quartics, they might be sine curves, they might be which they call sinusoidals. They might be root curves, okay, radical equations, that kind of stuff, which is a lot more objects than just what's seen in the linear. Does that make sense? Okay, but we've got 2 categories, linear and nonlinear, and then that nonlinear category has a whole lot of subgroups. But these types of statements here, these types of linear equations, are similar to all types of equations. Okay, we have what we call a conditional, an identity, and a contradiction. I just want to kind of go through and talk about what those things mean to us and why they're named what they are. Okay, so this one, obviously, you guys can solve this. What would x be if we solve this? X is going to be 3. Okay, so what we say is that this is only true when x equals 3, or only true on the condition that x is 3. That make sense? You guys remember talking about conditional statements in geometry, if-then statements? Okay, so if x is 3, then 2x minus 1 equals 5. Okay? Or if 2x minus 1 equals 5, then x equals 3. Okay? It is only true on that condition, on that requirement. Does that make sense? That's why we call them conditional equations. Okay? The next one is what we call an identity. Okay? Now, you all have identities, right? Okay, Lucas is always Lucas, right? Unless you're David. Okay, but you're always yourself, right? Okay. What we mean by an identity is that this thing here is always this thing here. Okay? Think about the algebra that goes along here, and this result is indicative of an identity. If I distribute the 2x minus 3, I get 2x minus 6 equals 2x minus 6, right? I distribute that. I could stop there, but we'll keep going. Okay, because this is obviously seeing that the left-hand side is the right-hand side, right? If I plug in any x value and evaluate the left-hand side, it will give me the same thing on both sides, right? Okay. But I could do this. I could go 2x equals 2x. I got to add 6 to both sides. And now if I want to subtract 2x from both sides, I get 0 equals 0. Okay. Does 0 always equal 0? Yeah, any integer is always equal to itself, right? Any real number is always equal to itself. So this is true. It's a true statement, and it is always true. Okay? So when you get down to a particular line in algebra, whether it's 2x minus 6 equals 2x minus 6, or you could have divided both sides by 2 at the onset instead of distributing, you could have gotten x minus 3 equals x minus 3. Whenever you get a statement that the left-hand side is identical to the right-hand side, you can stop and say, this thing is always true. This is what we call an identity. It says no matter what I plug in, the left-hand side will always be equal to the right-hand side. Is that all right, everybody? Okay, now you've seen some stuff, and we'll go back and graph these things, but you've seen situations in Algebra 1 where you would have identities. Algebra 1 is probably the last place that you guys really focused and talked about identities. Trigonometry, we'll talk about them a lot. This one here, it's called a contradiction. Contradiction. What's a contradiction? If I contradict myself, what's that mean? Yeah, it goes the opposite of what I said. Okay, so I might have given you a truth. Hey, we got a test on Friday. Okay, you show up on Friday, we go through class, we never had a test. Didn't my actions contradict what I told you? Right? So I've made something false. So if I go through here and I distribute my 1/2, okay, or what I prefer to do, I prefer to multiply everything by 2 here, but it's up to you what you want to do. If I multiply everything by 2, it's going to be x minus 1 equals x plus 4, right? Multiply that by 2. Those will give me 1. Leaves me just x minus 1. And come over here and multiply that by 2. Gives me x plus 4. Is that okay, everybody? Remove x from both sides. And negative 1 equals 4. Is that true? No, that's false. That's a contradiction. A lot of times, as you move on through higher level math, if we come to a contradiction, that's kind of the symbol that we use for contradiction. It's kind of the hashtag symbol or the pound sign rotated about 45 degrees. Okay? But that's a false statement, meaning there are no solutions here. Negative 1 is never equal to 4. Okay? So, no solution. So, there are some things that we can do graphically that might make sense here. And this is obviously none of those equations are really difficult to deal with, right? The graphs of these things are not going to be difficult to deal with. What I want you to understand is the concept of what we're doing with the graph. Because you might take the ACT here pretty soon, and you might come across some questions on there that we haven't discussed. Solving some equations that we haven't discussed. If you understand how to use your calculator to solve these equations, you can use your calculator to solve the ones that we haven't discussed. If you understand how to solve these with the calculator, I should be able to give you any inequality or equation, and you should be able to come up with a solution without having to do the handwritten work. Okay? So, first thing I want to do is just look at this example, and we'll go to the conditional one. 2x minus 1 equals 5. every single time that you come across an equation, that thing right there will produce a graph. Okay? This thing right here will produce a graph. The x value of intersection of these two graphs will be the solution to the equation. No matter what those graphs are, whether they're both linear, whether one's linear and one's nonlinear, or they're both nonlinear, okay, when I graph them and I look at where they cross, okay, and I look at the x value of where they cross, that will always be the solution to the equation. Okay? Now, when you do these on a calculator or any graphing tool that you have, you've got to write, this one's going to be y equals. Like if I'm on my TIA 384, that's y1. And I would call this one y2. And I would graph y1 equals 2x minus 1. And then the next line, graph y2 equals 5. I deleted my ROM on accident from my calculator, so I've got to find that. But I'll just grab GeoGebra here to prove this point to you. And I'll show you how to use Desmos as well. If I go y equals 2x minus 1, there's that graph, right? If I go, then the second one was y equals 5. I graph that. Okay. Now we did the algebra previously, and we found that the intersection should be 3. If I look at point A is where they intersect, and we said the x value of their intersection will be the solution to the equation, right? So if I come across an equation on an ACT that I have no business being able to solve, I don't know how to solve it, never seen it before in my life, I can graph both sides of the equation and see where they cross. Okay? So let me give you one that maybe you've never seen before. Let's say I take, let's go x cubed minus 1. So I'll write down what the equation would look like to us. We're going x cubed minus 1. Let's set that equal to, let's just say the square root of x plus 2. Okay? So we've already typed that in as y1. We're going to type this one in as y2. So those would be the two graphs. And you could do this on your TIA 3 or A4. You just go to y1 or y equals, type in those two things in y1 and y2. Okay? And you're going to get that image. Now that image on your TIA 3 or A4, it's kind of a pain in the butt, because on the TIA 3 or A4, if I want to be able to do this, so I want to drag and move it around, or I want to zoom in and zoom out, that's a very tedious process on that calculator. But on GeoGebra, it's just a click of a mouse and a scroll of the wheel to do those things. So that's why I prefer using this tool. But if I want to find out where they intersect, I click on the blue curve and then click on the orange curve. They intersect at 1.42. That is the solution to that equation on the bottom. If I were to take, now understand that that's 1.42. Now I go out to, 15 decimal places. It's really not 1.42, right? So what I'm going to do, what's nice about GeoGebra, just to check to see if I've done this right, like I can just say x of A. A is the point, right? If I hit x of A, it gives me that number right there. It cuts and pastes that number into now what they call A. Is that all right, everybody? So now I'm going to do this. I'm going to say a to the third minus 1. Well, remember, a is this thing. I'm raising it to the third, and I'm subtracting 1. So basically, I'm plugging that 1.418 into that thing right there, right? Does that make sense? There's a lot of different ways I can do this. But that's one way, and I get that quantity, 1.849. What should I get right here if I plug a in to that x? I should get the 1.849, right? I should get that same thing back. So let's go square root of a plus 2, 1.849. So that's validation that, yes, the x value that makes this statement down here true, to make this a conditional statement, the x value is 1.42, 1.418, whatever it was, and now I've got the solution. Now, understand, on the ACT, option A, B, C, and D probably aren't, none of them probably say 1.418. Okay, because there's probably, and I don't want to say probably, I know there is a solution to that that incorporates a radical. Does that make sense? So A, B, C, D is probably going to be the exact answer. If I have 1.418 as my answer, can I transform all those possible solutions into decimals and then match them up? Okay. If you, and hopefully maybe you know this or recognize this, the ACT could, honestly, if you know how to use, if you understand the conceptual aspect of algebra and how it works and how the rules work and the things that you can do to get solutions, kind of like this, where you've always solved equations, you've always gone through the processes, but we always had the understanding that what we get as an answer is the x value of where the graphs cross. Okay? If we have understandings like this, you should be able to do that ACT without ever having to write a single thing down. Okay? You could probably do it with just your calculator and the functions that are on your calculator. And you could probably do it in much less than 60 minutes. Okay? If we look at one of those equations, that second equation I gave you had like y equals 2x minus 6, and then it had y equals 2 times the quantity x minus 3. Now, GeoGebra will simplify things for me if I rewrite it in the way I input it. These look different, but are the graphs different? No, the graphs, no matter where I choose an x value, does that x value show up on both graphs? Yeah, so they always intersect. Okay? When we start talking about other functions like quadratics and cubics and stuff like that, we'll talk about potential numbers of solutions for equations. Okay? Linear equations, you have 0, 1, or infinite solutions. Here is a situation where we have infinite solutions. This is an identity. Okay? Because no matter what x value I choose, that one there is going to produce the same y value that one does. Okay? And the last one, I don't necessarily remember what it was. It was like 1/2, maybe x minus 1 or something like that. And then this one, 1/2 x plus 2. And we get something like that. Now, what are those two lines to one another? Parallel. They never intersect, right? Okay? Therefore, we have no solutions. That's where the algebra gives us a contradiction. So here's my question. What if I get, so now we understand that. Let's say I give you this equation. Let's say I ask, if I have x squared plus 1, when does that equal -3? Okay? And I ask you for the real solution. Okay? The real solution. Here's the idea. Hopefully you know what x squared plus 1 looks like. X squared is a what? What's the name of an x squared graph? Parabola. The plus 1 takes your x squared and it moves up 1 unit. So here's my x squared, and if I add 1, it just slides it up 1, right? Okay. Y equals -3 should be what kind of line? horizontal, through -3. Do those two curves ever touch? No. So do they have a solution on the real numbers? No, they do not. Now, you do understand, you do have exposure to solving that and getting imaginary solutions, right? Okay, getting things that have I in them. But if I'm just interested in the real solutions, there are none here because those two graphs do not cross. Okay? So those are all concepts that we can learn through an investigation of linear equations that carry over into other types of equations. Okay? There's some examples here. I have these. Okay? I teach this class at Rhodes periodically, and when I teach it at Rhodes, I do these questions with them because I have a wide range of abilities in that class. If you guys can't do this, I think we have issues. Okay, so my hopes are we can all solve those two equations. There are a couple on here that I want to get to. This one here, because this is a type of equation that people struggle with all the time, regardless of the level. I still have calculus students come back to me. Some of my best college algebra, trigonometry students come back to me in calculus, and they have these types of equations, and they're causing issues for them. So I want to make sure we can do these. Okay. All right. So example 3 here. And trying to address this, what should I try to do to solve this equation? Okay, make them all have the same denominator. That will work. So what will that denominator be? 12. Okay? So if I want to make them all have the same denominator, you're saying I need to multiply this one. So I need to make the denominators all 12, right? So let's see. Let me get this thing working. All right, so I would multiply this by 2 over 2, right? So you get 2x over 12. I'd multiply this one by 6 over, oh, not 6, sorry. Be 4 over 4, right? So it gives me 8 over 12. And this last one I'd multiply by 3 over 3, right? Okay? 9x over 12. Is everybody okay with that? Now what am I going to do? Huh? Okay. So there are several approaches here, guys, in the way we think about this, but my hopes are that you kind of realize that they all do the same thing. They're really all equivalent arguments. You're saying take out all the 12s. When you have all your denominators the same, okay, that means if this is going to be an equal statement, that means all your numerators have to be the same, right? If I gave you, I think there's one on the board behind me, if I gave you like x over 7 equals 3 over 7, what does x have to be here for this to be true? Doesn't x have to be 3? Because these denominators are already equal, so then what do I need to do to make the numerators equal? Okay, so that's the case that Blaze is making. This is dumb. I've got an undo, but I don't have a redo. Huh? I can't undo the undo. So what was this? 2x over 12 plus 8 over 12 equals 9x over 12. So like Blaze said, we can just wipe those out, and what we're left with then is a 2x plus 8 equals 9x. That will eventually give me, what, 8/7 to be my x? Okay? So that's one approach. That might not be an approach that anybody else used. Okay? An approach that I like to use, he said make all denominators go to 12, which is what we did, and we wiped them away, right? Okay? I think what you've probably seen maybe other times in Mrs. Cole's class was that you find the LCD, which was 12, right? And now multiply that by 12, that by 12, and that by 12. Has anybody done that before? Okay. So let's just kind of see what that ends up giving us here. Now, I want you to realize why we can do this. When I multiply by 12, I'm multiplying by 12 over 1, right? So I've got 12 times x, and then 1 times 6, right? Are those going to cancel right there? So 12x over 6, is that equivalent to 12 over 6 times x over 1? Can I break them apart that way? Now, the reason I know I can break those apart that way, because I know how I multiply fractions. And if I look at 12 over 6 times x over 1, I multiply straight across the top, I get 12x. If I multiply straight across the bottom, I get 6, which is equivalent to what I have there on the left, right? So I know that that's okay to do. I know I can break them apart that way. And that's the math that I want you guys to start understanding and realizing, because now you can do that division, right? That give you the 2x that we got the previous way. That make sense, everyone? Okay, now most people are not going to write it this way. Most people, because of the way you've been taught, kind of the monkey see, monkey do way, maybe we don't understand what we just or what we're about to do, but it's because of what we just did. If I look at this 12 and this 6 and I divide those, how many times does 6 go into 12? 2, right? So I should be able to cancel that 6 and do that. Does that make sense? Now, my hopes are we understand why we can do that. If I have x over 6, and I'm multiplying by 12, well, isn't 12 the same thing as 2 times 6? Right? Multiplied by x over 6. Those are a factor of 1. Correct? That's why they cancel out like that. And I'm left with just the 2 and the x. So I'm going to write down 2x. Okay? Over here, this 12 and that 3. 12 is 4 times 3, right? So the 3's will cancel, leaving me just that 4. Now I go 4 times 2 gives me 8. And now here, 12 again is 4 times 3. So the 4's will cancel, leaving me a 3. And 3 times 3 is 9x. That kind of makes sense? Okay? I think most people are probably, just in my experience over the last 13 years dealing with college algebra students, most people, when they bring me work, that's what they have. Okay? I'm not saying that's the right way. I like Blaze's way. That's fine. Because they're really the same thing. But I want to make sure that you guys understand you've been taught to do this, but my hopes are now we understand why. It's just the way we multiply fractions. Okay? You can multiply anything you want to by 1, right? Okay? Or I can take any equation, and I can multiply any equation by anything I want to, as long as I do it to all parts. Let's kind of view that real quick. Let's go to I just want to go back to like that real simple, like y equals, we have y equals like 2x minus 1, and we had y equals 5, right? The x value of that intersection is 3. Okay? Now I'm going to take this equation here, and I'm going to multiply. Give me a number.
700.
Let's go with 7. Okay? So I'm going to take y. So I'm going to y equals, I'll multiply that thing by 7. So 7 times 2x minus 1. Gives me a completely new line, right? So let's change that color. To blue. So we have that blue line. Now, I also need to change that one by 7. Does that make sense? Okay, so that one's going to be like y equals 35. And let's make that one blue as well. Okay? So now if I were to look at just these two blue ones, which would be those two blue ones there, right? If I ask where they intersect, is the x value still 3? That makes sense to everybody? So graphically behind the scenes, when I when I multiply both sides by something, or I subtract something from both sides, or divide both sides by something, I actually transform the graphs in the background. But no matter what I do, whatever these graphs end up looking like, okay, they will always intersect on that vertical line right there that has an x value of 3. Okay? So when we multiplied everything by 12, we really looked at an equation that was 12 times bigger than what we started with. Does that make sense? Okay? But that's perfectly fine. Can I multiply everything by 24? Yes. Okay? If 12 worked, which 12 is the LCD, okay? If 12 worked, then any multiple of 12 will work. 24, 36, 48, okay, 72. If I ever forget or struggle finding the LCD, the quickest way to find a common denominator, take that denominator, multiply them together, gives me 72. I can multiply everything by 72, and this thing will get back to just integer coefficients. Is that okay? Okay. You guys know why we multiply by the LCD? Huh? Think about this. Is that 6? Is that 2 times 3? That thing is 3, right? So I'm breaking this down to the prime factorization of these. That's 2 times 2. Okay? The LCD is to go through. Now, I say 2 times 2. Isn't 2 times 2 the same thing as 2 squared? When I pick out an LCD, I'm going to go through and I'm going to write down the factors that show up at least one time, and if they show up with powers that are greater than 1 or 2, I choose the one that has the greatest power. So 2 shows up, but here it's a power of 1, here it's a power of 2. So I choose the greater power. Okay? And then here I choose the 3. It's got a power of 1, that one's got a power of 1. Okay, so what's 2 squared times 3? It's 12. That gives me my LCD. But the reason we do that is because now that 12 is a factor of the 2 times 3. 12 is a factor of the 3. And 12, let's say it's a multiple. I'm using the wrong word, factor. Multiple. 12 is a multiple of the 2 times 3. 12 is a multiple of 3. 12 is the smallest multiple of 4. Does that make sense? So finding that LCD is finding the smallest multiple of all of those denominators, which will allow things then to divide evenly. Let's skip example 4. Let's do this one. What's that one called? What type of equation is that? Ratio equal to a ratio. Proportion. Okay? And how do you solve proportions? Cross multiply. Okay? Cross multiply 100% perfectly fine here. Let's do it. If I cross multiply, I'm going to get 3 times 2x minus 4, right? If you guys remember, those were referred to as the extremes for these ratios in geometry. Okay, I just want to take those two and multiply them. So I get 3 times 2x minus 4. Okay? Anybody remember what these were called in geometry? Those were the extremes. These are the... Come on, Chuck. M. Nope. What's a word for, like, statistics that means in the middle? And I said it. Mean. Okay? So these are means. Okay? Look at that, right? That's something we can do? Cross multiply, now I get, what, 6x minus 12 equals 16x plus 12. And I'll let you guys finish that. So I'm multiplied by cross products, okay? Using the proportion idea. Let's do this. Let's go through the route of using an LCD. What's the LCD? What's the least common denominator here? 12. So if I went through and multiplied this by 12, and then multiplied this by 12, what's going to happen with that 12 and that 4? Cancel, leaving you how many? 3. So now I have 3 times 2x minus 4. If I multiply this by 12, that's 3 and that 12 are going to cancel. You leave me 4. Now I have 4 and 4x plus 3. What do you notice here? Same thing? So when I cross multiply, and this is something this is very important for proportions. When you cross multiply, you're just effectively multiplying by the LCD. That's all you're doing. Okay? So those are, obviously, the structure and the way we wrote it is different, so people think they're doing something different. But algebraically, when you multiply both sides by 12 here, or you cross multiply, you are effectively doing the exact same thing. Is that all right? Okay. What do I multiply everything by there? 30. Okay, that's the LCD. I'll let you do that one on your own. Let's come down here to number 7. 7 is a little bit different. What is the difference in 7 that none of the other ones have shown yet? Yeah, there's a variable in the bottom. X is in the bottom. So, because X is in the bottom, we must approach this completely different, right? Right? Well, what's X represent? A number, right? X is just, we just don't know what that number is. So do I treat it different? No, and that's another thing that I want you guys to understand mathematically. Your variables are numbers. We just don't know what they are. So whatever approaches that you've been using for numbers, they're the same approaches that you use with variables. So instead of multiplying the bottom just, or I guess each fraction by an LCD that is purely numerical, which if I ignored all the variables, what would my LCD be? 18, okay? But now because there's a variable down there, I got to use 18x, right? So multiply everything by 18x. I like to write it that way. Some people are going to prefer if I have 5 over 2x minus 8/9 equals 1 over 18 minus 1 over 3x. Some people will do this. And they'll say, okay, well, we're going to cancel here and leave me with 9. I get 45. We're going to cancel here and leave me 2. And I just think that process gets kind of messy because you're not sure what the 9 and the 2 and that kind of stuff went to. So I'm going to try to use this technique all the time. Gives me 9. So you get 45. Now that gives me 2x, right? The x's did not cancel here because there's not one on the bottom. So anyway, minus 16x. It's going to give me x. And that's going to give me 6. And then again, I think that's one that you guys can finish on your own. But the idea, because x is just a number, it is like, so if x was, let's say x was 5, okay, then my LCD that I'd be using there would be 90. Does that make sense? Because that 5 would have to show up along with the 18 that's already there, so my LCD would be 90. But because I don't know what x is, it might be 5, it might be 7, it might be whatever, I'd treat it just like any other number that would have shown up down here. So what happens, this looks like a rational expression, or a rational equation, because we had variables in the denominator. But after a little bit of algebra, we recognize that ultimately it's just 2 lines that are intersecting that. If I can find out what those 2 lines intersecting are, then I automatically know these things where they intersect. Okay? That being said, like if I were to graph this, and here's hopefully an interpretation of the algebra that makes sense to us. If I were to graph these initially, I have 5 divided by 2x minus 8/9. Okay, that is not a line. Would you agree with that? Okay? There we go. Okay, that thing is not a line. Okay, we call that a rational function. The other one, the other side, 1/18 minus 3/x. Okay, that is not a line. Make sure I got the right one. 1 over, oh, this is wrong. Okay. But if I ask for the intersection of these two things, why is it not working? There we go. I get the x value of 3. Okay? Now, if I go back to, what do we have here? We had 45. So multiply everything by 18x. So it's sort of 45 minus, 16x. And then the right-hand side, what did the right-hand side turn out to be? X minus 6. Okay? If I ask for the intersection of that one and that one, what's the x value? 3. Still 3, right? Okay. So we transformed. We went from, through the algebra, we went from these two nonlinear curves, that one there and that one there, and transformed them into ultimately a linear equation, and the solution to that linear equation is the same solution to this nonlinear equation. Does that kind of make sense? Okay. So every time that you do something to an equation, you are transforming it, you are changing it, and therefore the graph behind the scenes changes, but the solution to that graph behind the scenes, as it changes, that solution should still be a solution to the original. Okay? Let's see here. Let's do this one. Now my denominators are binomials, right? Yes. Okay. Now, and this will be something that we'll have an entire chapter dedicated to working with equations like this. But my hopes are that this is an easier one. But whenever you have denominators like this, okay, remember these represent just numbers, right? Okay. Now remember when this was like a 6, and that was a 4, and I think at one time this was like 3, then I break that down to 2 times 3, that to 2 times 2, and that to 3 times 1, and I picked off the factors that were new, right? Well, you have to do the same thing in a situation like this. Okay, this is x plus 2, that's x minus 2, those are factored. But is that factored? No, you have to do the factoring process here. And this thing is going to be x minus 2, x plus 2, isn't it? And now if I want to create my LCD, I go through here, and I'm going to say, well, x plus 2 is a new factor. That needs to be part of my LCD. Is x minus 2 a new factor? Yeah, it's not x plus 2, so that needs to be part of my LCD. Are either of these new? Nope. Nope. So I go to each one of these, and I multiply by those factors, and now I'm going to have 7 times x minus 2. I'll have plus 5 times x plus 2, and then these cancel completely, right? So I have 10x minus 2. So did that now turn into, once I distribute that 7 and that 5 through, did that turn into strictly a linear equation now? Where initially, if I were to graph that stuff up there that was provided in the original problem, that's an ugly, ugly graph. But if I graph that stuff that I have blue at the end, it's much simpler. It's 2 lines. Okay? So my hopes are that we start to understand that procedure in regards to, in the process of mathematics. My task for us this year, my main goal, is not for me to do something and then you to mimic it. Okay? Because then you can only do the things that I do, right? Okay? My task for you, my goal for you, is that you learn the system. You learn the ins and outs. You learn the properties. You become inquisitive and ask questions like why and how come and that kind of thing. And then you take the initiative to produce a reason of why or how come. So then when you get to an authentic problem, one that's completely new to you, you can approach it, okay? Because who's in physics? Okay, in physics, you're going to come to authentic problems, things that are completely new to you, okay? But if you understand the algebra that governs physics, you should be able to address those things and determine what equation or what formula you're supposed to use. Okay? Yes?
Do we have any homework?
No homework tonight.
Oh!
Tomorrow we're going to get into solving some quadratic equations. So there will be some homework with tomorrow.